HA2, in this module of video is going to be exploring what we refer to as radical functions. And of course, we would refer to anything that is a function and has a radical. Essentially, we're going to say there's some radical quantity on the right where the independent variable is inside of the radicand. This would be considered to be a radical function. So would actually the cubed root of x, that would be a radical function, or a fourth root of x, or fifth root of x. But specifically in this video, we're going to be looking at the radical function that has a square root called the square root function, and the radical function where it's a cube root, which we call a cube root function. And so these two parent functions, you notice that it says the parent functions for a square root and cube root function are listed here. So the parent function for the family of square root functions says here is y equals the square root of x. I'm going to write this a little bit more large. So we'd say that this is the square root function, and over here we have y equals the cube root of x. This is y equals the cube root of x. Its graph right there. So let's just recall in the past we memorized 4 families of functions here, and it was worth our while to know what their parent functions graphs look like so that we could sketch their transformations very easily. So we have our constant function here, and we said that this was any graph where it was just y equals some constant c. We also had y equals x, and we referred to this as the identity function. Identity or linear parent function, also linear. We have also y equals x squared. This was our quadratic model, quadratic family of functions, and this was our one that started at 0, 0, goes through 1, 1, okay, as this one does over here. But it also goes through negative 1, 1, and then also 2, 4, and negative 2, positive 4. And this looked like a u. And then last but not least, our absolute value parent function, y equals the absolute value of x. So why go through all of this? Sorry, here it goes through 1, 1. Because what I want you to see is this. If you know the shape of the parent function, and you know that all of these, with the exception of the constant function here, the parent function goes through 0, 0, and 1, 1, then essentially all you need to do is memorize the basic characteristics of the graph and the basic domain and range, and you can sketch any of the functions in that family knowing your transformations very well. So let's take a look really quickly here at our square root function and our cube root function. And what I want to do is I want to encourage us to make a table down at the bottom of both of these. And so whenever you want to make a graph, obviously one very easy thing to do is just make a table of values. So for our square root function here, I'm going to write this. I'm going to write, let's go negative 1, and then we'll go 0, and I'm going to go 1, and actually I'm going to go 4, and I'm also going to go 9. And so the reason why here is because when we plug in these x values in for the square root here, so for instance, if I want to go find f of 0, I would say it's the square root of 0, which of course the square root of 0 is 0. When we plug in 1, if I were to plug in a 1 here, I get the square root of 1 is 1. The square root of 4 would be 2. The square root of 9 would be 3. So you notice that I chose convenient values of x that I know the square root of. And then also here, I'm going to say not real. The thing here is we can only take the square root of numbers that are 0 or bigger. So when you look at the graph of this, look at the graph of these points here. We have 0, 0s on the graph. Also 1, 1 is on our graph. We found the point 4, 2, but that is this point here. And if we were to go out 9, we would certainly be up 3. It'd be right around here. And so you can see that it's getting bigger and bigger, but it's not doing so at a quicker and quicker pace. It's kind of leveling out. And so we have this graph that only exists for x values that are greater than or equal to 0, and its domain and its range is also only y values that are greater than or equal to 0 there. Okay, so cube root graph, what we're going to do here is we're going to plug in negative 8, negative 1, 0, 1, and 8. Sorry for the discrepancy in color here, but if we said the cube root of 0, of course the cube root of 0 is 0, the cube root of 1 is 1, the cube root of 8 is 2, the cube root of negative 1, believe it or not, is negative 1. The cube root of negative 8 is negative 2. So if we put all these points on our graph, what I want everybody to see here is this. It does start at 0, 0, and it does go through 1, 1 as our parent functions do. Both of these functions do this. But instead of just going up and to the right, kind of like a half of a sideways parabola here, we also go down and back and to the left. And you can see how negative 1 is also on this graph here. And we get this graph that's really stretched out from left and right forever and ever. And so its domain and range is all real numbers. So what I want you to see is this. You need to memorize the basic shape of both of these graphs here. Square root is 0, 0, 1, 1 and goes over to the right. And then the cube root is 0, 0, 1, 1, but also down 1, left 1, and goes left and right forever and ever. So what we want to do is we want to generalize our transformations here. And of course, these are transformations that we've seen before. I would say generally speaking, we have some parent function f of x, and that every transformation of this function really is some stretch value, or it could be a reflection, times the function where we plugged in some h value and we have some loose k on the outside. So we'd say that, recalling that this is our vertical translation or vertical shift here, and it is honest. Honest in the fact that if it says +3, your graph shifts up 3. And then this here we have our horizontal translation, and it is dishonest. So horizontal translation, I'm just going to write a liar here. It misrepresents itself. And then we have our stretch, and I want to be clear on this. If it's out in front here, we say this is a vertical stretch. And also sometimes it could be a reflection here if we have a negative value out in front. So let's talk about these transformations. Now, we've generalized them before, but we say horizontal translation, shifting left and right. You notice here that we have our value here, or h value here, on the inside of here with the x. And so whenever the h is associated with the x here, we know that this is a horizontal translation. And keeping in mind that if this says -2, we're actually going 2 units to the right. And if this says +3, we're going 3 units to the left. And so that's kind of going with what I mentioned over here about it being dishonest. So vertical translation, of course, this +7 or this -1 here, notice it's on the outside of the radical. It is not on the inside of the radicand with the x. Then we would say that this is our vertical translation. And of course, this would just be exactly up 7 units and down 1 unit. And reflections. Okay, so here's the interesting thing about reflections. Remember, if you make your x value negative, that would show up inside here in front of the x clearly. You would have a y-axis reflection. But if you make your y value negative here, which actually shows up out in front of the radical, then it reflects over the x-axis here. So the last thing to mention is horizontal stretch and shrink, vertical stretch and shrink. I would say that this a value over here that we call the vertical stretch and shrink here, that's really what you see a lot of the time. But this is a number out in front that we're just multiplying this by. This is our a value here. And so we can see that right here, this being a 4, it's going to be vertically stretched by a factor of 4. This is a fifth here. It's going to be stretched by a factor of a fifth. So it's either away from or towards the x-axis. When you see horizontal stretch or shrink, this is, I'm not going to say it's uncommon because we're going to look at a couple of examples here, but this is when you are multiplying your x values times some constant here, a. And it's clear because it always shows up on the inside right next to your x value as a coefficient of x. So that being said, with respect to that coefficient, if it's ever horizontal stretch or shrink, remember it's by a factor of its reciprocal. So since this is a 3, it's actually going to shrink by a factor of 1/3. And since this one's a half, it's actually going to stretch by a factor of 2/1. So let's take a look here at when we would apply these transformations on a function. So let's graph each of these functions and identify the domain or range for each one. So here's what I know. F of x equals the square root of 1/3 x. What I want to say is this: if we were to look at the parent function, that would just be this graph right here. So knowing that the parent function starts at 0, 0 and goes through 1, 1. As a matter of fact, the square root graph, I just want to kind of point this out here so you get used to it. We say 0, 0, 1, 1, but plug in 4 because we get 2. We'd say 4 2's on this graph. You kind of see how this looks like a half of a sideways parabola that opens upward like this. So here's our f of x, I just want to show you this, equals the square root of x. If you wanted to graph this function here, what I notice is that I'm taking my x value times 1/3. So what this is a horizontal stretch. And I say stretch because it's by a factor of its reciprocal, factor of 3. So what this means is the new graph hasn't been shifted, but it is at 0, 0. And instead of going through 1, 1, it's going to be 3 times as far away from the y-axis here. And this one here, this 4, 2, was 4 away from the y-axis. We'd have to go 4, 8, 12, clear out here. But basically, we would get a graph that you could see is horizontally stretched by a factor of 3. So let's take a look at this next example here before we end this video. But g of x equals -2 times the cube root of x. So when we look at this here, let's go ahead and admit something. At least we know what the parent function looks like. And so this cube root function, again, I'm going to advocate for putting that on there before you do anything else. We'd say it goes through 0, 0, and 1, 1. Now recall that this graph goes through -1, -1, and this is that kind of sideways graph that does that there. I want to say that also if we were to make a table here, x, y, -8, negative 1, 0, 1, and 8. I choose these because they're cubes, but you get negative 2, negative 1, 0, 1, and 2 as the cube root of all of these numbers here on the left. So we'd say if we go left 8, 1, 2, 3, 4, 5, 6, 7, 8, and down 2, this point's on our graph just like positive 8, positive 2 is on our graph. So this is just a representation of our parent function here. What we would like to do, this is our y equals the cube root of x graph here. What we want to do is apply this transformation here. And I notice that this is a value out in front that I'm taking times all of this. So this is a vertical stretch. And I know it's a stretch because vertical stretch, you know, is just kind of whatever it is out front that you have there. That's what you're multiplying by. And 2, well, 2 is bigger than 1. I mean, you're going to get bigger. And also it has a negative there. So I know that this has an x-axis reflection. So it has an x-axis reflection, and it is a vertical stretch by a factor of 2. So what we're going to do is this. First thing is we're going to apply the reflection here. So if we were to apply the reflection over the x-axis, then that would mean that this point here at 1, 1 would now be down here, and this point here at negative 1 would be up here over the x-axis. 0, 0 is going to stay the same, and then these points out here are also going to reflect over. So our reflection over the x-axis would appear like this on our graph. Now the other thing is that we are stretching this by a factor of 2. So I'm going to switch my color again here, maybe more to like an orange color. And we say that this was also vertically stretched by a factor of 2. So vertical stretch is away from the x-axis. So this would still be at 0, 0, but this here would be twice as far away from the x-axis as it currently is. It's 1 away, now it's 2 away. This is 2 off the ground here below the x-axis. Now it's 4 below. So we're going to shift these now twice as far away as well. And we can see that we get our finally transformed cubic function. It was reflected over the x-axis and is vertically stretched by a factor of 2. And we would say this is the cube root of negative 2 times the cube root of x. Cheers.